is Zakharevich, whose talk title is Decompositions of Varieties, Birationality, and P-Theory.
Hi, so I wanted to start by thanking the organizers for inviting me and all of you for coming to listen to me. I'm going to be talking about doing scissors congruence with varieties. So what do I mean by scissors congruence? I mean, if you take a variety, you can, so let's take two varieties, very simple, P1 and A1, disjoint union of point. These are not isomorphic. However, you can decompose them into pieces so that they become isomorphic. So you can think of P1 as the union of A1 and a point. You can think of this as the union of A1 and a point, and then the pieces are isomorphic. So these are piecewise isomorphic or scissors congruent varieties. And if we want to try to analyze varieties up to piecewise isomorphism, this is a very difficult thing to do because varieties are sort of geometrically difficult things to work with often. I mean, this is difficult enough if you're working with nice, simple geometric shapes like polyhedra. This is even harder with algebraic things. So to do this, to try to analyze these kinds of problems, we introduce an algebraic object that will encode some of this information. So this is the Grothendieck ring of varieties. Which is K0 varieties, is the free abelian group generated by varieties. And there's a base field floating around. I'm not going to be worrying about it too much in this talk. This talk is actually, I think, almost completely going to be independent of the field. So if you want, you can assume that it's the complex numbers or whatever your favorite field is. And then we're going to quotient out by the following relation. Whenever we have a closed embedding of two varieties, we're going to declare that x is equal to y plus its complement. So this is saying that a variety is the same as a decomposition. And you can see that if two varieties are scissors congruent, that scissors congruent lets you decompose each of the varieties into the pieces, and then this tells you that they're going to be equal in this ring. The ring structure, I haven't told you the ring structure yet. It's not really going to matter for this talk, but in the interest of completeness, we're going to define the ring structure to be given by Cartesian product. So in a certain sense, this encodes all of the information of scissors congruence. But unfortunately, it actually destroys some information too. I just said that if two things are scissors congruent, then they're going to be equal. But the converse is false. It's entirely possible for two things to be equal and for them to not be scissors congruent. And I say this as though this is obvious, but we only there's a paper from 2000-something, 12, I forgot the date, and I forgot to write it down. I'm sorry. So anyway, it's a result of Borisov that there exist varieties x and y such that x is equal to y, but x and y are not scissors congruent. And this is very recent. I think it's 2014. So it's a very so this ring, on one hand, we know that it encodes some of this information, but we don't know exactly what. And the ring itself is quite difficult to work with. It has uncountably many generators, uncountably many relations. It has zero divisors. That's a result of Poonen. It has zero divisors. And in fact, the class of the affine line is a zero divisor. And this is, again, Borisov. So it's not a pretty ring. But we still want to work with it because it's the universal invariant that satisfies this. And we have a lot of invariants like this that we like cohomology with compact supports and whatever variety of cohomology you like for varieties. And so we want to be able to work with this. We want to be able to say, if we can understand this ring, we can understand all such invariants. All invariants like Euler characteristics or cohomologies. And so understanding this ring would be great, but all of these properties make it seem like a very difficult proposition. And what I propose, so I'm a topologist, so I look at this 0 and I go, why is that 0 there? There shouldn't be a 0 there. It should be like an n. These should be like the homotopy groups of something, and that something should give us more information about this. And in addition, that information should tell us something about how this K0 behaves. So I want to give an example of what I mean by this. So we can define a group. There are no colors. OK, so we can define a group like this, where we say, OK, well, we have on the set of generators, on the set of varieties, we have a filtration by dimension. And so we should be able to define a group like this, where we have the free abelian group generated by varieties of dimension less than or equal to n, modulo the same relation. We have an obvious map, K0 varieties to dimension n going to K0 varieties. And in fact, we can sort of compute the graded that this gives us. And I want to put graded in very strong quotation marks. So you should think of the quotation marks as being bigger than the word. Like, we can calculate this rather easily. So what's this? Well, you look at all your generators, and you kill all of the generators of relations of dimension less than n. And then you look at this relation, and assuming, for instance, that x is irreducible, y has to be of lower dimension. And so what this says is y is going to be 0 in that quotient, and this says that x is equal to a dense open subset. So what you have here is this is actually the free abelian group generated by the birational isomorphism classes. Of dimension n. So if we knew that this was an injection, then we'd be able to say, oh, well, this gives us a complete associated graded to this filtration. Like, this would mean that this gives you a filtration on K0 var. We have an associated graded. It's free. This tells us a lot of information about the ring itself. Now, unfortunately, what Borisov's result means is that this is not injective. So where could elements in the kernel in this come from? Well, so imagine that you have two varieties of dimension n. And these are not scissors congruent. So they're different over here. And now you say, OK, how can they become equal once they're included into something of much larger dimension? Well, suppose that they both sit inside some variety W of much larger dimension. And suppose that we have a birational automorphism. So we have a birational automorphism from W to itself. So this is an isomorphism from U to V, such that the complement of U is X, and the complement of V is Y. Then the relation tells us that X plus U is W, that Y plus V is W, and this isomorphism tells us that U equals V. So both X and Y are equal to W minus U, so they are equal. They have become equal because of this birational automorphism. This is not necessarily injective. It's just, but you can quotient it. Yeah, think of it. I'll say by the image of this. You know, it's going to be some subgroup. It's an abelian group, so you can quotient out by it. Yeah, we don't know that this is injective. If we knew they were all injective, the whole thing would be injective. But so you can get things like this that make things go wrong. So now we have a whole bunch of questions. Firstly, can we get some control on what's going wrong? Can we find a way to nicely algebraically encode these are all the things that can go wrong and nothing else will go wrong? So for instance, are these kinds of things that come from birational automorphisms the only things that can go wrong? Maybe there's something else that can make this kind of injectivity go wrong. Is there some way to fix this filtration? Is there some way to make it a filtration? I mean, it's not. We know that it's not, which is why, by the way, I put the n in here and not on the outside. But is there some context in which this becomes a filtration? And it turns out that all of these things can be answered if we, instead of thinking of K0 var as a ring, start thinking of it as the connected components of a space or a spectrum, if you're happy with spectra. Because, for example, it is entirely possible to have a filtration on a space which is not a filtration on its connected components. That's totally fine, and we have tools for dealing with that. Filtrations on spaces lead to spectral sequences, and the spectral sequences have differentials that control how far away the associated gradient of the filtration is from the data on the whole space. So both of those things will give us the tools to be able to analyze these kinds of problems. But now the question becomes like, how do we do this? What is the correct way to create a space? I mean, there's sort of a silly way of making a space, which is make a point for every element of this ring, put the discrete topology on it, there's a topological space, but that space won't give you any more data than we already had. We want a space with more data. We want one that remembers the geometry of what's going on and encodes it in some nice way. So as motivation for what I'm about to do, I'm going to give a very quick 5-minute crash course on algebraic K-theory with a focus on the things that make it similar to what's going on here. So let's see. So I'll call it an aside on algebraic K-theory. So if we have a ring R, we define K0 of R to be the free abelian group generated by finite dimensional, let's say, projective modules over R. And we're going to quotient out by the relation that whenever we have an exact sequence A to B to C, we're going to declare that B is equal to A plus C. So we have this. And then we're going to say, OK, this gives us a lot of information about the ring. But for instance, all fields give you the same thing. So clearly, it doesn't remember all the important information about the ring. So we can construct other K groups. We can, for instance, define K1 of R, which is usually defined as the abelianization of GL of R. So this is all matrices which are going to be the identity passed outside of a finite region. And then you abelianize that. And so you think of this as, in terms of our context, in terms of what we're talking about, these are automorphisms of R modules, sort of all nicely packaged into one thing. And then you abelianize it, and there's a lot of good reasons for it. But I will only give you one good reason for it, which is you want this to be the place where the determinant lives. And the determinant is abelian. So you sort of, and when R is a field, this actually becomes, this becomes R cross. So it actually is the determinant. So you sort of want it to be the generalized form of that. And then there's formulas for K2 that I'm not going to go into, but the analogy I really want to emphasize is you have these automorphisms here, which contain important data, and we are seeing automorphisms showing up there, which are also containing some kind of important data. So maybe these are not. here, you can do projective, you can do not projective. They're going to be the same if R is regular or something, something, something. There's good conditions on it. You can do not projective, and then there's a measure for the difference, and I don't want to go into that. This is the sort of classical way of introducing it, so this is where I'm going to stick for now. Bounded. It's all finite. It's just we're trying to package all modules into the same thing, and so you let yourself pad your matrix by identities. Okay, so these are the kinds of things that the analogies I want to emphasize. So maybe you can see that the two things are not distinct. You're saying, okay, here we have A including into B. C is the complement of A and B in this kind of situation. And we're declaring that B is A plus the complement in exactly the same way that we're doing it up there. And then in the traditional algebraic K-theory, you have K1 groups which contain information about automorphisms, which look like they're sort of similar to these kinds of things that are popping up. So maybe this kind of makes sense as an analogy. And I say this just so that it's not completely out of the blue when I'm about to start constructing K-theories. So if we just have these tools, how do we construct Kn in general? So one of the reasons I don't go in to write down the classical definition of K2 is that it doesn't actually help in figuring out how to construct Kn. So here's how to think about how to construct these Kns. We have this combinatorial data of finitely generated projective R modules. This data has combinatorial information about how it can be assembled and reassembled. What we want to create is a space that remembers that combinatorial data, where the connected components of the space will remember sort of these classes of what can be reassembled into what, and where paths will remember ways of taking something apart and reassembling it. And that's sort of what these automorphisms are doing. So that's the construction we want to make. So here's how this is done. You look at the category of modules over R, and I mean finitely generated projective. And you notice there are two kinds of ways of seeing that a module is smaller than another module. So we have two kinds of ways. We have the inclusion, and we have the surjection. So if we say that A is, I'm going to put this in quotation marks, is a part of B, if A is a submodule of B, or if A is a quotient of B, or a composition of these. So what we're going to do is we're going to define a category whose paths are formal compositions of these. And then we're going to say that paths in this category are what give us our space. So we're going to define, this is going to be Q mod R. And the objects here are finitely generated projective R modules. And a morphism from A to B is a formal composition showing that A is smaller than B. And if you want to get completely formal about it, you need to not just take these. You want to take the quotient by, you want to take equivalence classes of these, where if I take a module here, and then I take an isomorphic module that sits the same way inside B, I'll say, oh, they're the same thing. But this is what we're saying. We're saying a way to get from A to B is an expression of saying A is less than B. And in order to be able to say you can put any kind of path of these, any kind of formal composition of these into just a single span like this, we need a way of commuting them past each other. So the observation is that if you have A, I'll call this C and I'll call this B, and suppose you have a composition of these in the wrong order, we can commute these past one another by taking the fiber product, and this is going to be, and this is a way of saying this formal composition is the same as this formal composition. And this makes sense because the kernels of these are the same, and the co-kernels of these are the same. So it's a perfectly reasonable way of saying, oh, well, this composition is the same as that composition. And now we can get any formal composition of these kinds of paths into a span that looks like this. So this is our category, and now we want to construct a space where paths in this space are going to be compositions of these. So we're going to take the nerve. So this means we have 0 cells, which are objects. We have 1 cells, which are labeled by morphisms. A 2 cell is labeled by a composition. So we have A to B to C. Oh, apologize. To C, and we attach this as a triangle. So this is A to B. And then this is B to C. And then this is the composition A to C. And then 3 cells are labeled by A to B to C to D, and so on and so forth forever and ever and ever. And then we define the K theory of R. This is as a space is loops on, I suppose I should call this B, not N, because this is not a simplicial set as I've defined it, BQ mod R. So this is, and the theorem is that K0, so pi 0 of K of R is exactly K0 of R. Pi 1 of K of R is exactly K1 of R. And so it makes sense to define Kn of R pi n of K of R. So this thing that I wanted to get a space where K0, remember, has this information, and the higher K groups, remember how modules are put together and decomposed, that's exactly this space. So part of the goal of what we want to do now is we want to say, OK, we have this well-developed picture. This is, by the way, Quillen's work from the early 70s. Developed picture for how to do this for rings, and a well-developed literature saying this is a useful thing to do. And what we want to do is we want to translate the lower boards to the upper boards. We want to be able to say the same things for varieties in the same way in order to get a similar space that will encode this kind of information. And then we want to extract useful information from that space. So the trick is in constructing this category somehow. Yes? So we have a 0 module, which is a sub-module of everything. So pi 0 is trivial. But if you want, if you want to get the connected components, since you asked the question, I'll spend a couple of minutes answering it because it's a good thing to think about. So why do we need the loops? So for any module, we have two morphisms. From the 0 module to A. We have the one represented by 0 surjecting onto itself and including into A. And we have the one represented by A surjecting onto 0 and then being equal to itself. And these are different. In this category, I said that it's only if you choose isomorphic things that they're going to be the same. And assuming A is not 0, these are not the same. So on one hand, we have a path from 0 to every object. So pi 0 of BQ mod R is just trivial. But pi 1 has an element, which is you start here, which is the base point, and you go around this way. Right? This is two parallel morphisms. We're going to go forward along one and backward along the other. And we're going to say that A is that path. And then what's going to happen is that you can show that the relation that you want, B is A plus C, whenever you have an exact sequence, arises from several 2 cells glued together. So so that relation will hold, and in fact, it will be everything. It requires some proof, and I don't want to go into it, but you should. I can give you a good reference. It's very nicely explained in Weibel's book, for instance. But as a moral explanation of why you want it to be loops, that relation up there is a 3-term relation. 3-term relations are induced by triangles, not by lines. And so if you want a 3-term relation, you really ideally want to be able to glue in a triangle expressing that relation. Now that's 1 dimension up. That's a 2-cell, not a 1-cell. So we somehow need to pull the 1 cells down to the 0 cells. And that's what we do with loops. So that's sort of the moral explanation about why you should expect to have a loops in there. And almost all constructions of algebraic K-theory will end up with these loops precisely because we start off with a 3-term relation. OK. Other questions, just so that I'm not steamrolling over people? OK. So what we want to do is we want to do this, but with varieties. Now, in order to have these kinds of things, you need to, for instance, have a notion of exact sequence, which we don't have for varieties. And you need to have a notion of, in fact, usually for an exact category, a category where you can do this, it needs to be an additive category. The category of varieties is not an additive category. You might want to have a 0 object. Category of varieties does not have a 0 object. So on one hand, it feels like, OK, trying to do this exact same construction with varieties is just a lost cause because we don't even have the basic data to start to work with it. On the other hand, while all of that is true, a lot of that is in there because you want to be able to prove things. So Quillen has his famous theorems of Davisage and localization, which are really wonderful theorems allowing you to analyze the K-theory of rings and other exact categories. And they're very powerful, and a lot of what he needs in those constructions is in order to prove those, not in order to do the basic construction. All you need in order to do the basic construction is what is currently on the board. So let's look at what's on the board. We have a category with objects with a notion of inclusion, of smaller than. We have 2 of these notions. And we have a way of commuting them past each other. Notice, however, that we never actually compose a surjection and an injection. And this makes perfect sense because our surjections are going backwards and our injections are going forwards. So we never actually compose them. So what we need to be able to do this is two families of morphisms which express less than, and a method for commuting them past each other in such a way that the complements in both directions are going to be the same. So I'm going to start by doing this with finite sets. And with finite sets, it's going to seem a little bit funky. But, ooh, colors. This is going to make it so much easier. So it's going to be, I'm going to try to do it with finite sets. And with finite sets, it's going to seem a little bit funky. But then I'm going to move on to varieties, and you'll see why there's honestly two different kinds of inclusions that behave differently. It's just that with finite sets, it's a little bit easier to get our hands on at first. So what I'm going to do is I'm going to talk about finite sets and two kinds of inclusions that say that a set is smaller than another set. So we're going to define the K-theory of finite sets. So notice that we have objects, which are finite sets. And we have two kinds of morphisms. I'll call them yellow morphisms and orange morphisms. We have the yellow morphisms, which are injections. And we have the orange morphisms, which are injections. But there are two different kinds of injections. There's the yellow ones and the orange ones. And now what we need is this way of commuting them past each other. Now, greater contrast. OK, let's try. Is that better? Green? OK, yellow and green. OK, is that better for people? Yeah. I'm happy to do orange and green. People want me to do orange and green or whatever? No? OK, whatever. I'm sticking with yellow and green. People can deal. So we have two kinds of injections. Now, one of the things I really want to point out is that these two went in opposite directions, but injections go in the same direction. So we're going to need to be working with that a little bit. So what is a way of commuting an orange injection, a yellow injection past a green injection? What does this even mean? So let's say I'm going to do yellow first and then green. So let's say we have A, B, and C. And we have a yellow injection here and a green injection here. We want to complete these to a square in such a way that the complements in this direction are the same as the complements in this direction. So what I can put here is A union the complement of C and B. And I can say, OK, so then I'm going to declare this one to be green and this one to be yellow. And now the complements of the yellow injections are the same, and the complements of the green injections are the same. So now I can define Q of finite sets to have objects finite sets. And for those of you familiar with K-theory of finite sets, I want to really emphasize these are not pointed finite sets. These are just finite sets. And then a morphism is from A to B is a formal composition of a green injection and a yellow injection. And green injections and yellow injections cannot be composed, because we're thinking of them as analogous to surjections and injections going in opposite directions. To commute them past each other, we use this rule. And now you can compose green with green and yellow with yellow, and that gives you a perfectly well-defined category. And we're going to define the K-theory of finite sets to be loops on BQ finite sets. And this gives you the correct definition of K-theory. by the correct, I mean there's other ways of constructing the K-theory of finite sets, and this gives you the same answer. Just as a quick comment, for those of you familiar with the Waldhausen S-dot construction, which you usually use with finite pointed sets, this actually gives you an isomorphic result to that. It's just a different way of encoding the data. Okay, so we have that. So now we need to say, okay, so how can we do this with varieties? It's easier to see the analogy here than previously, but we can define for varieties, we have two kinds of morphisms, which are closed embeddings and open embeddings. And now we can do the exact same thing. If you have a closed embedding and you have an open embedding, we can actually write down the exact same formula. And you need to think of it as a subvariety of Z, which it is. But this is, and this works. And this is going to be a closed embedding. And this is going to be an open embedding. And now you can do the exact same thing to define the K-theory of varieties. So now we can define the K-theory of varieties to be loops on BQ of varieties. And in fact, you can check, in fact, exactly analogously to the way you prove in Quillen's case that K0 is what you want. You get that pi 0 of the K-theory of varieties is exactly K0 of varieties. And why can we think that this is sort of a correct way of defining these? Again, there's the silly way of defining K0 where K-theory of varieties, where we just said, oh, take the discrete topology on the Grothendieck ring. And we said that's not going to give us more information. How can we be sure that this will give us more information? Well, because this actually remembers how varieties are put together. It's encoded in the structure of the space. All of the paths in the space, all the one cells, are actually encoded by ways of including a variety as a locally closed subvariety of another variety. The relations are describing ways that if you included, x into y and y into z, it remembers that it's a way of including x into z. So it remembers all the different ways you had of pulling varieties apart. So it makes sense that this space should remember important information about, say, automorphisms, piecewise automorphisms of varieties. And if we quotient out by lower dimensional varieties, that should remember things like birational automorphism information. So this is sort of the morally why this should be the correct thing to do. I also just want to comment, there's sort of historically, even if there wasn't any reason to think that this is going to produce something useful, K-theory has historically produced a lot of interesting connections between things. So just sort of pushing this kind of thing is a useful thing to do. In general, by the way, a category where you can do this is a CGW category. So it's a place where you can do this kind of Q construction. The most general place you can do it is a CGW category. And it's just the data of the CGW category is the two families of morphisms and the data of how to commute things past one another. And the thing that happens once you start thinking about things in these kinds of terms is the same kind of magic that happens with Quillen's results. Quillen has this definition of an exact category, which has these beautiful theorems. For instance, if you look at the definition of K0, it makes sense that if you have, well, I don't want to do it in terms of a ring, but you have a bunch of objects and a subset of those kinds of objects. But you can filter any of the larger set by things in the smaller set. You should get the same K theory. This is called Decompositions. It's a big theorem of Quillen's that says, formally, if you have a category and a subcategory, it gives you a good relation for when the K theory of the subcategory is the same as the K theory of the category. Decompositions is magic because it doesn't really work for anything other than exact categories. It's somehow, Quillen's proof is half a page. And it looks like, well, this clearly should generalize. But it's somehow, I'm a really big fan of this proof. I don't know if you can tell, but it's just very beautifully encapsulates exactly what needs to happen to make this work. And so there's a lot of effort to generalize this to other places where people do K theory, like Waldhausen categories. And it just doesn't work because Waldhausen categories don't give you enough of a grip on objects. And Quillen actually uses the additive structure of what's going on to make this happen. But once you start writing things down like this, there's magic that happens because both of Quillen's theorems work in CGW categories. And I'm slightly lying because Quillen's only work for abelian categories. CGW categories are a generalization of exact categories. So it makes sense that you need a few more assumptions that are analogous to abelian categories in order to make the theorems work. But you can make them work. I mean, and pretty much what you need to assume is everything has a kernel and a co-kernel correctly. And when you write that down appropriately, what ends up happening is that Quillen's theorems work. And I don't just mean his theorems work, I mean his proofs work. Like, you look at Quillen's proofs, and somehow you translate them into these kinds of, you have these two formal kinds of morphisms that you can't compose, and you start translating into that way, and it just works. So Quillen's Decompositions and localization, which are tools for analyzing K theory, also work on CGW categories. So in particular, they work for varieties. And I just want to really point out how magical this is. Grothendieck has this dream of motives, that there's a universal cohomology theory on varieties, that there's a universal map from varieties into an abelian category. And a lot of his motivation for this is that the category of varieties behaves like an abelian category in many ways. And so really there should just be a small amount of modifications you should be able to do to it in order to sort of make it the universal abelian category. When you start thinking about it in terms of CGW categories, what you see is the category of varieties is already an ACGW category. It behaves like an abelian category because when you encode how abelian categories behave from the point of view of decomposition, they behave identically. So in that sense, it's not a huge surprise that these theorems should work. But on the other hand, it's kind of a huge surprise that these theorems work. Am I supposed to end early and give time for questions, or do I go up until 11?
I think it's up to you.
Okay. So let's see how to use these theorems. In the thing that I erased over there, I said that when we work with just the Grothendieck ring of varieties, we can compute the nth filtered part mod the n minus first filtered part. And we get a very nice simple answer. It's the free abelian group generated by birational isomorphism classes. So what we want to do is we want to use Quillen's theorems to do the same thing, only on the whole space. So the first observation is that dimension gives a filtration on K of var. Now, at the beginning, we discussed that it doesn't give a filtration on K0 of var, but it gives a perfectly well-defined filtration on K of var, and you can just see what's going on. The subcategory of n-1 dimensional varieties is a proper subcategory of varieties, up to dimension n and up to dimension n-1. That's just a subcategory, honestly. And then when you start constructing the B of the category, you have 0 cells are labeled by objects. That's a subset. 1 cells are labeled by morphisms. That's a subset. 2 cells are labeled by compositions of morphisms. That's a subset, and so on and so forth. So you get subspaces between the classifying spaces of the categories. And then when you take loops, well, some loops are going to land in the subspace, and some loops aren't, and that's going to be your subspace. So it's an honest filtration now. And so we have an honest filtered space, and so if we can compute the filtration quotients, we will get a spectral sequence converging to the homotopy of these. So the next step is to try to compute the filtered quotient. So we have k var n mod k var n-1. And what is this? So first I want to say Quillen's localization. And Quillen's localization says the following thing. If A and B are abelian categories, and A is a Serre subcategory, so that you can define B mod A as an abelian category, then K of A, including into K of B, projecting down to K of B mod A, is a homotopy fiber sequence. I mean, Quillen didn't use the term homotopy fiber sequence, but this is what he meant. What this means is that if you have a subcategory and you can analyze the homotopy type of the K-theory of the quotient, you can get a long exact sequence like this. So it turns out you can define all of these terms for CGW categories. And what happens there is that you get the exact same kind of thing with a different definition of what this quotient is. And I don't want to go into the details. What I want to tell you is the inclusion of n-1 dimensional varieties into n-dimensional varieties satisfies this. Serre subcategory pretty much means closed under precomposition. So if you have a variety that's dimension at most n-1, any subvariety of it is of dimension at most n-1. And you also need that if you glue together two varieties of dimension at most n-1, your result is a variety of dimension at most n-1, which is also true. So this is what it means to be a Serre subcategory in this context. And so now the question becomes, what is this? And because I only have 10 minutes left, I don't want to go into the details of how you do this analysis. And I'm also going to put a note that this is as spectra because I don't want to write down the formula for what happens with spaces, which is a bit more complicated. But this is the wedge over alpha in B sub n. Remember, this was the class of birational isomorphism classes of degree n. So you wedge over these you take the classifying spaces of the birational automorphisms of alpha, so meaning the automorphisms of any birational automorphisms of any representative. You add a disjoint base point, and then you take the suspension spectrum. You can construct a formula like this for spaces. It's just a little bit more complicated, and it doesn't actually add anything to comprehension. So this is what I want to point out. Morally speaking, it decomposes as a sum of classifying spaces of birational automorphisms. So In particular, pi 0 of this, because you had this disjoint base point and then took the suspension, because pi 0 of this is going to be z. So pi 0 of this quotient is a z for every alpha in birational automorphism classes, which is exactly what we got before. So at least in that sense, we are doing the correct thing. But we now have a spectral sequence that's converging to the K-theory of varieties. So we should be able to say what the differentials are. And in particular, we can say very explicitly what the differentials from the thing converging to pi 1 to the thing converging to pi 0 is between those two columns or diagonals, however you want to grade this thing. So an element in pi 1 of this is element in the abelianization of the birational automorphism groups. So pi 1 of B birational is Z mod 2 plus the abelianization of this birational automorphism group. And the differentials ignore Z mod 2, and they take, so let's suppose that we have some phi in birational of the class of X. So we can think of phi as an isomorphism from U to V, where these are both open subsets of X. Then the differentials take phi to the complement of U in X minus the complement of V in X. It's doing exactly this thing that was over here where I said, okay, what is the thing that can go wrong? You can have a birational automorphism of something much bigger, and it can induce this relation between the complements. This is exactly what the relation that the differentials enforce. And this is the only relations that differentials enforce. So in fact, this question I asked at the beginning, do we know that this is the only kind of thing that can go wrong? This spectral sequence says, yes, this is the only thing that can go wrong. Nothing else, no other kinds of relations are enforced. But in addition, we can already see, okay, pi 1, K1 of varieties, is going to be somehow put together out of these abelianizations of birational automorphism groups. You can also see, for instance, if a birational automorphism has a model where it's an actual honest automorphism, then the differential will be 0. Because we just calculated this on a particular choice of representatives, we could have chosen that representative, and it would be 0. So the differential on any honest automorphism, or anything that can be modeled as an honest automorphism, will be 0. By the way, I would love to know what these are, or what they look like, or anything at all about them. So if anybody is interested and or wants to tell me a whole story about these, I would love to hear it, because I don't know anything about them. But we do know some things about them sort of from secondary characteristics. We know there are non-zero differentials. If there weren't non-zero differentials, then in fact you can prove if all differentials are 0 between these two columns or diagonals, however we're grading this, then it is the case that if x equals y, then they are piecewise, then they're scissors congruent. Given that we know that's not the case, we know there are non-zero differentials. We don't know where they are, but we know that they exist. We know that we can, given some results about limits on dimensions, we can compute that these are 0 for low dimensions and only start being 0 being non-zero for higher dimensions. But we can also actually analyze the structure of this spectral sequence to do some slight generalizations of other results. So I'm going to say a couple and then finish. So first off, there's a theorem of Larson and Luntz, which says that if you take K0 varieties, and this is for the base field, this is over C, and you quotient out by the class of the affine line, then you get a very simple thing. You get the ring generated by the stable birational isomorphism classes of projective varieties. And you can do this, and Larson and Luntz have a very hands-on proof of this. It's a six-fold iterated induction, iterating over several things. You can actually get this by, you can get a similar spectral sequence for quotienting by multiplication by A1, and then you can actually see the differentials quotienting out by stable birational things. So the rth differential will quotient out by the difference between two things that are birational after multiplication by a to the r, but not after multiplication by a to the r minus 1. And so when you go to the infinite page, you've quotiented out by all stable birational equivalences. And so you can reprove this in a nice geometric way just studying the structure of the spectral sequence. But you can also do the following, which is, at the beginning I mentioned that Borisov had these, I cited him for two results. One was for saying that the class of the affine line is a zero divisor, and one was for saying that there exist things which are equal in the Grothendieck ring but are not piecewise isomorphic. And it's interesting. So it's a beautiful 6-page paper where he proves both of these statements. And his goal, the paper is called "The class of the affine line is a zero divisor." And the goal of the paper was to prove that the class of the affine line was a zero divisor. And then at the very end of the paper, there's this comment, as this other person points out, this also gives an example of two things which are piecewise, which are equal in the Grothendieck ring but are not piecewise isomorphic. So this was a complete coincidence that he managed to prove both of these in the same paper, because he was aiming for one and his example happened to work for the other one. And the reason I put "happen to" in quotation marks is because it will always happen. So the theorem is given x minus y in the annihilator of the class of the affine line, x cross A1 and y cross A1 are not piecewise isomorphic, assuming they are chosen to have minimal dimension. Yes, A1 is important. The reason people are interested in this annihilator is that if you want to define, for instance, motivic integration, which has values in theory in K0 varieties, you need to actually invert the class of the affine line in order to make it well defined. And so there was a big question of, okay, but are we killing information, or is this localization just sort of adding more stuff? And proving that it actually is a zero divisor means you're actually killing quite a lot of information. I don't think so. Because, actually, let me think. Right, you can't, because what this theorem uses is it uses that any birational isomorphism can be, the weak factorization theorem, that any birational isomorphism can be factored as a bunch of blow-ups and blow-downs. And that's where A1 is really playing a role. If there was a similar theorem for something else, it would work for something else. But I don't think there's a similar theorem for anything else. And that was what I wanted to say.
We started a couple minutes late.
It feels like there should be. I don't actually know what it is. That's a question I've sort of looked into, but I haven't been able to find anything yet. All the differentials out of k0 are 0. I'm not sure if that's the question you're asking.
I guess that's the question I'm asking.
Yeah, all the differentials out of k0 are 0.
Does your proof of the Larson-Luntz result use k equals c?
It does, again, for just, it uses the weak factorization theorem. All of this holds anywhere where the weak factorization theorem holds. So you don't actually need k equals c. You just need field of characteristic 0. And if people could show the weak factorization theorem for prime characteristic, then all of this would work for all primes. I don't remember if, so there's, in the paper where I do this, I define a notion of a convenient field where the precise thing that I need works, which is that if you have any birational automorphism, then this difference lands in the ideal generated by the affine line. That's the only property you actually need. So any field where that is true, this will work.